Okay. So good afternoon, everybody. Just to start off with, how's the semester going? Tough? Good? Easy? How's the semester going? Nobody is listening or what?
Hello.
Yes.
Tough, sir.
Tough, huh? This
Yeah.
course is tough or whole semester is tough?
Sir,
The
I'm in my
semester.
final year, so placements are also.
Ah. And that too, this class is right in the evening. All of you had classes up to this time also, up to 5?
Yes, sir.
So just a recap that there is a first class test on Monday at the Monday class slot, 5 p.m. It will be a 1-hour test and the coverage will be till tomorrow. Whatever is covered till tomorrow. We'll give you an idea of the format and submission pattern and everything tomorrow. But so those details we'll let you know tomorrow. So let's get started. So now we have been started to discuss introduction to uncertainty. So based on the classes that you'll have had on Monday, can any of you tell me what are the, where does uncertainty arise in economics? Where does uncertainty arise?
Where there is risk involved.
So one is risk. Can you explain this with an example about what do you mean by risk?
Yes, sir, I can explain it by using the financial markets.
Tell us.
Like if we invest in a stock, let's suppose, and we long that stock, like we think that the stock will go up, the stock prices will go up, but suddenly anything could happen and make that stock price go down. So there is risk of losing our money out in that case.
Right.
So there
So
is
that means,
uncertainty.
so here you're saying that you are expected to get some return and some period of time, and this is your for every investment decision there is a return, there is time. So let me erase all this. So you have taken an investment decision I1, you can take an investment decision I2, etc. But the outcome of this investment decision is not fixed, right? That's what you're saying. Outcome of investment decision is not, how would we call it? Is not fixed, let us say. It's not deterministic. Yeah. So if it is not deterministic, how would we model this?
Using probabilities.
Right. So one is probabilistic modeling. How would you use probabilistic modeling? That means instead of having a fixed outcome at this point, your outcome at this point will be, this is time, this is a range, lower range of return, this is an upper range of return, or you can also say that instead of saying this, I will have return, the return versus time may be a probability distribution, right?
Yes, sir.
And that too, it is going to be also modifiable. Sorry. By events, as you just said. Other than time, there can be events which could cause sudden jumps and falls. Is that okay to everybody? Anybody has any other suggestion on risk? Does anybody have any other suggestion on risk? If you don't participate, no, then it becomes difficult for me to take the class. I can finish off in 10 minutes. Anybody else has any other suggestions? Kartikeya, Mike, are you there? Kartikeya? Not there. Deepankar, Sajdeva, are you there?
Yes, sir.
Anything else? Any other thoughts of how uncertainty can come?
Thinking, sir.
Last day, Professor Pulak Mishra, in his slides, it is there, no?
Sir, uncertainty can also come from things that are not under our control. For example, for a farmer, the production level would depend on certain things like rainfall, and it's hard to predict the rainfall for the upcoming year.
So that one is risk, which is uncertainty. I don't know what will happen. The other, as you said, is environmental or uncontrollable variables. Right? Is that what you said? The uncontrollable variables are usually modeled as an environment, as the others party. So this is modeled as an environment which is the other party. You model all your conditions. You can model them independently, or you can model them together as a clubbed entity. Okay. Who said this?
So Pankuri.
Yeah, Pankuri, is this understood?
Yes, sir.
These are uncontrollable variables. Variables which you do not have control of. Anybody else? Anything else?
Sir, policy changes.
Policy changes, what do you mean? Who is making the policy changes?
Government.
So policy changes are changes with the rules of the game. Yeah. And there's another very simple case. Other agents, other competitive or collaborative agents, no?
Yes, sir.
So, you know, you don't always get to decide what will happen. Either, as somebody said, that if you take a decision, there is some chance that something else will happen, which is risk. I press the brake of a car, 99.99% chance the car will stop, but there is that 0.001% chance that the brake will fail. So that is risk. Environment, as somebody said, that I am trying to do something and the rest of it, that means I say that if I sow seeds, if I pour so much water, I'm expected to get this much of production, but rainfall may not come, Sunday locusts can come, etc., which is environmental action. The other is that you are in a bidding process where everybody is competing to obtain something. So there are other parties. Correct? Anything else? Anybody else has got any other thought? Sunidhi, are you there?
Yes, sir.
Any other thought?
No, sir, I was also thinking about the market.
Okay.
That comes under competitive bidding.
Very good. So how do we model uncertainty in our search paradigm? In our search paradigm. Let us first talk about modeling uncertainty in our search framework. What does the search framework have? What are its features of the search framework?
State.
Very good. State
Transformation rules.
State transformation rules.
And goal state.
Start.
And goal.
And costs. Correct? Is everybody with me? Please participate, otherwise
Yes,
the fun is lost. Now tell me, where is uncertainty? How do we model uncertainty?
Sir, it's in the state transformation.
First in the state, tell me in the state. Let us say my state has got variables S1, S2 up to Sn. Now where is the uncertainty?
Sir, the uncontrollable factors.
No. Before that, so let this state be S. This is my state set. I have a subset T of S is observable. Correct? My observable states are only a subset T of S, which means that I have got partial information of the situation. Give me an example in economics.
The playing cards.
Economics is not playing cards. Give me an economics example.
Sir, but it's a game.
A game, everything is a game. Chess is economics. You must be able to translate it to this domain, na?
Sir, insider trading.
Insider trading. Very good. Anything else?
Sir, repo rate.
Repo rate. What do you mean? What about repo rate?
Sir, we only have a finite amount of repo rate changes that we have seen so far.
No, I'm talking about the state. You are the person who has to take a decision. Now, give me a problem in which there are n state variables and you can only see a few of them. You have got a set of variables. You can only see a few of them.
Sir, what about consumer behavior?
Very good. Consumer behavior. Very good. Consumer or user behavior? So what do you have about consumer behavior? You may have only aggregated information, right? You may have average, you may have something, and you will not know the behavior of every consumer. You will only know certain information. The data that you have will be insufficient. Anything else? Think about it. I will not tell you unless you start thinking. We will not get to, you all must start thinking. Otherwise, you all will only learn state space and not economics, because that is what is our objective. I thought about it. I realized that I must get you to think about economics. So I want somebody to think and let me know what is it that I want to observe? What is my full set of state variables and what is it that I'm only able to see? That is very important. So I leave it to you to think. I'm not going to tell you anymore nowadays. Second is on state transformation rules. This one is a little easier for you to do. Where is the uncertainty?
So the state we are going to achieve, that is uncertain.
Correct. So
after applying the transformation.
So your action, all actions are not controllable by you. You can take an action A. You have options of taking action A1, A2, but the outcome of the action will depend on just what Pankhuri said. It may depend on the environment. It may depend on opponent. Because the next few actions that can happen is not in your control. By the time others take action, whether it's an environment or opponent, and your chance to take an action comes, this is your next chance. The states that you have come through for an action that you have taken is, you may know the set of states, but you won't know which one will come. Is this clear?
Yes, sir.
So there are two places of uncertainty. One is incompleteness of information. The other is that other than you, there are other agents who also take action. This is how we model it. So we model it in two forms. One is incompleteness of incompleteness or incorrectness of information. This is modeled at the state. That means if there is a state S, state set variable state description S, you can only see T. The second is about actions of other parties, including quote unquote, we club environment, risk, state. So this is modeled in the state transformation rules.
Sir, isn't it the reaction of the opponents and the other parties is also incomplete? Like,
yes, everybody is incomplete. Nobody is playing a fully complete game. Is that clear, Abhishek?
Yes, sir. So that isn't that can also go in the state?
Yes, everybody sees some T dashed. Everybody sees some T dashed.
Yes, sir.
So it's a situation where there are multiple agents and everybody is trying to take some decision, and that is where arises this dynamical situation. And it could be discrete, but in most economics cases, it is a then there are other things. There are other things which have come up in recently in economics, which is again very difficult to model in a state. Can you tell me what it is? Listen to this very carefully because this is an open field. There isn't too much of even research on this. So it is good for you to participate.
So could you repeat?
So behavioral finance.
So, you know, these concepts like sentiment, behavioral pattern, emotion, these have gained a lot of ground and people are trying to model all of this in economics. Now here comes a very difficult concept because the value to the variable that you give, you are also not sure whether how good it is. For a state, when you are assigning a value to a variable, that value is also unclear to you what you're saying about that value. He's happy about it, he's unhappy about it, he's very happy about it. Got it? So this also comes in state and state transformation rules modeling, because in the state you don't know what to say, and in the state transformation rules it may be just a bifurcating judgment. Have you seen these advertisements which are coming up on this Zomato and this and that, and suddenly something is happening? Isn't it? Are we okay? Good.
Yes, sir.
So now we come back to see what we are going to do to model this. We already described it a little. So what we model is we use the concept. Hey, Utkarsh, you can't hear me? I think Utkarsh, others can hear, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So, so the way we will do our modeling, is we will use what is called and or graphs. And or graphs are like this. There are two kinds of nodes in a graph. Or nodes and let us say and nodes. Or nodes, this is when we model the state transformation rules. Or nodes are where the agent who is taking a decision has a choice of which decision, action, rule segment to apply. For example, the decision maker of RBI they can decide that what is going to be the next repo rate now. Whether I will increase, decrease, keep it same. If I increase how much percentage point, I may have some 10 options. The other is for this is the AND node is where the decisions are taken by others and the agent who is solving the problem has no control over. That means that if I am the OR node is my RBI, then once I increase or decrease the repo rate, whether the banks will follow it, whether there will be a more investment in the market, etc., etc., how much will it be? Those are not in the control of the bank decision maker. On the other hand, on the RBI, on the other hand, for the decision maker of the bank who is going to decide on lending rates and this, that, etc., the new fixed deposit policies that they are going to make, what are the additional incentives they are going to do, they have no idea. They have no idea that what the bank is going to do, RBI is going to do. And therefore, they will assign certain probabilities on RBI decisions. And in here again, when there are 5 other banks, each bank will not know what the other can do, especially the private banks and the public banks. Yes, what is it that people have posted on the chat box?
Sir, I posted an example of uncertainty of in the economics, in which the Cristiano Ronaldo in a press conference moved the Coca-Cola bottle which were kept in front of him on the side, and within a few minutes, Coca-Cola lost $4 billion in stock market.
So that is event. That is event.
Yes,
and
yes.
That relates to sentiment.
Yes, sir. Sentiments. That's exactly what you said. No, it impacted the sentiments so badly nobody could have predicted it or
So these are unpredictable sentimental events which are very common in economics.
Yes.
Very good. So now when I model this, then earlier I had a state, I had some state spaces, I had next states, I had some more next states, and I was trying to find a path to the goal. But now I have a situation like this. I can take certain action, then somebody else will take certain other action. Then again I can take some action. Again somebody else, here this may be one or more parties. So I model this as what I called an AND node. And I model this as what I call an OR node. And now, while I can choose which one of the left or the right to go to, I don't know which one the AND node will take. I can guess. So I can then, given the AND node, I can work out the worst scenario. I can work out the expected scenario. So what I work out depends on the problem at hand. Are you all getting an idea now? Animesh Jain, are you there?
Yes, sir.
You're getting an idea, no? So
Yes,
I have made this move. So therefore, the whole thing turns out to be a generalized game. And it turns out to be what is an AND OR graph or an AND OR tree. But it may be more than one player. It may be player with environment. There may be cooperation, collaboration, competition, all of them inbuilt. But the basic modeling talks about this modeling. So how do we draw up game trees? We draw up a sample game tree like this. So there are two kinds. One is the box node and one is the circle node. The circle node, let us say, is my node and the box node is my opponent's node, or the box node is my node, circle node is my opponent's node, for whatever. Now suppose I've opened it up. Therefore, this is my node. This is environment or other node. Again, my chance, then other chance. This other can be, why we model it as a normal game, but it could be anything else. And at the end, here are the outcomes. Let us say here are the outcomes. I've just drawn a 2-level game, but you could open up the game up to as many levels. And once you open up the game to as many levels, then if it is my node, will it be or AND? Vidyut Mandal?
Yes, sir.
Will it be or AND if it is my node?
And
My node will be AND. My node is one where I am taking a decision, right?
Yes, sir.
An opponent's node is where I have no control over the decision. So now I can assume 2-3 things. One is I can assume that the worst thing will happen to me. So if the worst thing happens to me, then what is the best I can do here? Can anybody tell me what is the best I can do? Which side should I try? Which move should I make, left or right? So which move should I make, left move or right move?
Sir, in the first level, I should make a left move.
In this top level?
Yes, sir, I should make a left move.
Everybody agrees? Why can anybody, does everybody agree that I should make a left move?
Yes, sir.
So can you tell me why?
Sir, because maximum payoff there is 10, which is there on the left side of the the tree.
Mm-hmm. Is that the case? Anybody else? What will my opponent try to choose here? Here, let us name these nodes A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Just tell me,
if you go
at
right
node
here,
F, node F is my opponent or my choice?
It's my choice.
Node F, node F.
It's my opponent's choice.
So my opponent will try to make which move? Worst for me or best for
number? For worst for me.
Worst for me. At node G, it will be worst for me or best for me?
Worst for me.
How much will it be?
6.
6. At node D, what will it be? Which side will I go?
The 6.
6.
The right side.
So at node H is 1. At node I is 4. At node E is how much? Ashutosh, Animesh Jain?
Sir, 4.
4. At node B, it will be what? How much?
4.
4.
Are you all getting the hang of it now? Now let us come here. At node L, what will it be?
1.
At
1.
node M?
3. 3.
At node J?
3.
3.
At node N? 7. At node
7.
O? 8.
8.
At node K? 8.
8.
At node C?
3.
3.
3. At node A? 4. And
4.
therefore, as somebody said, the left hand side is better. Now, did you get an idea why the payoff is not 10?
Yes, sir.
Huh?
Yes, sir.
Yes, sir.
So now when I make this move, I really don't know what my opponent will play, but I know that as of now, 4 is the best. Now, the question arises that after I play 4, my opponent can play left side or right side. Once my opponent plays left side or right side, I will play accordingly. So my solution is that clear? So my solution is no longer a path, but my solution is this. I will do this. My opponent can do this, which is an AND node. Then once my opponent does this, I will do this side. If my opponent goes to E, then I will do this. And then my opponent can do any one of them. So I will end up with either 4 or 6 or 8 or 10. This side. Got it?
Yes, sir.
Now, so every solution is what? At the OR node, I take one of them, and at the AND node, I take all of them. So I actually get a subgraph of this graph, of which in this option, my worst case is 4 and my best case is 10. For another tree, my worst case can be something else, which will be lower. My best case could have been higher. Any questions till now? Another solution could be I take this side, then my opponent can take me to any of these sides. Then I take this side and I take this side. Then my solutions could be this one or this one or this one or this one. So I have a set 3, 5, 8, 9. Whereas in this one, my set was 6, 8, 4, 10. These are my solution possibilities that I can get up to this point. Now, once I do this, I can add what? What else can I add to this? Instead of doing worst case, best case, I can add
Expected
probabilities. I can add probabilities. And there are 2 places to add probabilities. Can anybody tell me where I should add probabilities?
Second tier.
That means I will add probability B to D and probability B to E. And obviously, what will be the property of PBD plus PBE?
Difference in sum should be 1.
Is expected to be 1, right? Otherwise, I have to model other, which I don't know. Then again, I will model every edge of my opponent with probability. If I know the probability. Is that clear to everybody? Priyanshu Pandey?
Yes, sir. It's clear.
So
Sir,
now, yes, question? Yeah.
Yes, sir. So why we have taken the right path, like you have told, like we will take the right path. Then if we will take, like, then after that we can take every path, like you have taken the 3, 5, 8, 9. Even we can got other one like 1, 5 or 7.
Yes. So why we took their right path is because in the worst case here I will get 4. Here I will in the worst case get 4 and here in the worst case get 3. The right path at A, the path, this path at A does what? It maximizes my worst case. Got it?
Yes, sir.
Now, once I have probabilities, then associated with every leaf node, what will I have? The path probability.
Yes, sir.
Associated with every leaf node, I will have the path probability. And from that, I will calculate what?
Expectation.
So I will have an expectation here. And I will have an expectation here. And based on that, I may decide to use expectation. Correct? So my solution is no longer a path, but a subgraph. And if I'm doing worst case analysis, then I will use, I will find that whole set of solutions on every subgraph. And then if I'm doing worst case, I will find the worst. If I'm doing expected case, I'll find the expected. Vaishnavi, are you okay?
Yes, sir.
Now, there is another place to do probabilities. Where can you tell me? We just discussed it a little while ago when we discussed risk.
So to model the risk appetite of the player at the odd node.
No. This one, instead of being a value, the leaf node, instead of a value, can be a probability distribution, right? It will say that it can take this value with this probability. Instead of a fixed value, it can take a value with a probability. So it can be a probability distribution. Is that clear?
Yes, sir.
Yes, sir.
Along with that, it can be even more complex, that instead of just a probability distribution, it can model many other things. So it can be a very complex model instead of just a value. And once we have all this in place, we have a new way of solving these, and new algorithms, new search algorithms can come up. Many of these search algorithms are not explored yet, and they are open for So you can model the leaf nodes as the final outcome, which would be uncertain. And you can model actions of other parties as uncertain. And by combining these two, your solution is a subgraph. And every leaf of the subgraph could be a value or a distribution. And depending on the opponent, which could also be worst case or probabilistic, and depending on what you want to do. So here again, your own sentiment. And then somebody just pointed out a very interesting thing. At your own level, you may want to take a risk. That means you may want to take a decision with a certain probability. So I leave it to you to think of how this thing can be modeled. We won't have time in this course because we have got many other very interesting topics after this module. But I hope you have got an idea of what to do. Shriman, are you there?
Yes, sir.
Okay. Are you getting an idea of what to do?
Yes, sir.
So among the ones where I want to maximize my worst case, that means I want to find my best worst case, we compute what is called the minimax value. That means if I am maximizing, as we just computed a little while ago, I find out at my nodes. So these are my nodes. These are other nodes. These are my nodes. And these are other nodes. And let us see. So I want to really compute 4. My question is, what will be my search algorithm to compute 4? Observe very carefully for the next 5 minutes and participate with me. And you will get the hang of what I want to say. So I start with this node, and this is the first node that I see. And I start applying depth first search. In depth first search, what do we do? Can anybody tell me? Shivam Naik?
Sir, we go deeper and deeper unless we find the leaf.
We use a stack and we go deeper and deeper. So after seeing this node, I go and see this node. Then I go and see this node. Then, sorry, let me not number them. Then it gets confusing. I see this node. Then 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 I see this node. After seeing this node, I tentatively say that this is 2. Are you all with me?
Yes, sir.
Then I see this node. And then I back this up and this 2 remains 2 or becomes 6.
Remains 2.
So I say my tentative value at its parent is 2. Are you all with me? Stop me if you don't understand, because this one time you understand, you're done. We are doing DFS. We are back to search now. Then I see this node. Then I see this node. Then I see this node 6. Then I see this node 8. And the value remains as 6. And what happens to this value of 2? It now becomes
6.
6. And I put 6 here. Then I come and see this node, which is on the right. Then I see this node. Then I see this node. Then this becomes 1. Then I see this. This remains 1. This is 1. Then I see this node. This becomes 4. Then I had come here. I see this node. This remains 4. What happens to this node now?
It will become 4.
It becomes 4, isn't it?
Yes, sir.
Then its parent becomes 4, isn't it?
Yes, sir.
Yes, sir.
Then its parent becomes 4, isn't it?
Yes, sir.
Yes, sir.
Then I see this node. Then I see this node. Then I see this node and I come here. Then this is backed up as 1. And here I have an interesting situation. What is the interesting situation? Has everybody got up to this point?
Yes, sir.
Right. Right. So now the interesting situation is at this node, the value is 1. At a parent above it, the value is 4. Do I need to see the right hand side of this node whose tentative value is 1?
No, sir.
Again, others. Abhishek has said no. Others? Tushar?
No, sir.
No, sir.
Why I do not need to see this node? Why I do not need to see this node?
So because we are maximizing the risk, just like 4 is the maximum from here.
Yes, so because this is my opponent node, it will minimize. So it will always go below 1, whatever is this side, whether it is 0 or whether it is 5 million, it will never increase beyond 1. Got it? On the other hand, here I have already got a solution of 4. So there is no point in seeing below this. So this is my pruning of my depth first pruning. You remember current best kind of pruning we used to do? The current best kind of pruning. Here I can do this pruning. Is everybody clear now? Anybody who has not understood? Anybody who has not understood? Tejasvi, are you there? Tejasvi?
Yes, sir. I understood.
So now what is backed up here in the parent?
Sir, 1.
1.
Now I come to this node and I look at this and what is backed up here? 3. Now what else can I do? Because this is 3. And what can I do? I'm looking at this 3.
We can prune the other part.
We can prune this part. Suryansh Kumar, is that clear? Everybody, Suryansh Kumar. Vaibhav Prasad, are you there?
Yes, sir.
Is it clear?
Yes, sir.
So this now backs up what? So this becomes 3, right?
Yes, sir.
And the backup
Yes,
value
sir.
here is 3.
Yes, sir.
Now, anything else we can do?
Sir, prune the whole left,
Sir,
right
put up-
side.
Yes, sir.
Yes, sir. Prune the whole thing.
So I have applied my current best, but now my current best is the current best at my node and my current worst. That means the current best of my opponent. So now I compare the current best of myself and the current best of my opponent. And if my current best is better than or equal to the current best of my opponent, I can prove. So now I have evolved my depth first branch and bound to this. And this, anybody knows the name given to this algorithm in game trees?
Algorithm.
Pruning.
So this is actually DFBB, depth first branch and bound. Now you can apply MDepth branch and bound, you can apply hundreds of things. Then what will be A star equivalent? What would be IDA star equivalent? That I don't want to do now, but I just want to tell you that all of this is possible. Because we don't have enough time to do all these, but you all can take it up as assignments and things like that. And finally, when we come to probabilistic, which we have already discussed, when we come to probabilistic situations like this, then we have to, what do we have to do? Can anybody just recap? We have to find solution subgraphs. What is a solution subgraph? My node is OR node and opponent node is AND node. And in this AND node, I will compose. And based on every solution subgraph, I compute. What do I compute?
Expected value.
Expected value. And this expected value may be a single expected value or maybe values with probability also. It could be a distribution also. And then I will try to either get the best of my option, or as somebody just pointed out, depending on the amount of risk I want to take. So for me, I will take a risk-based decision. And for my opponents, I will take a expected distribution. What are my algorithms to do all that? Is a little more complicated. I don't want to go into that, but I want to give you an idea. This is how we can do our modeling. I will stop here for today and we'll do a different kind of modeling tomorrow. Any questions?
Sir, in the risk-based decision, can we also consider that we will take a decision which will maximize our best possible case?
Yes, yes. Right. Now that risk-based decision, your choice is how you choose from that expected distribution that comes up here. So some expected distribution D1 will come here and something will come here. Now it is your choice of what you want to do, how much of risk you want to take.
Yes, sir.
You know, this is a very neat way of doing things and a very nice algorithmic way of doing things. You all will learn even more complications when you discuss game trees, auctions and things like that. But in terms of state space, this is a reasonable way of doing things. Veda Vittal, are you there? Vittal Agarwal, we can't hear you.
Yes, sir, I'm there.
So we'll stop today. You can stop the recording and then we can figure out what to do. We'll meet again.